Hello all. So we have been talking about models that are used for signal integrity, right? So and then we have talked about the IBIS model. IBIS model is nothing but the input-output buffer specification model, right? So the basic model is used for modeling the I/O circuit of the IC, and this is what is predominantly used in the simulations. And if you are using hyperlinks, this is what is used for your simulations, right? So now, other than IBIS model, we hear about the S parameter model. So, before going to S parameter model, what we need to understand is in the IBIS model, what we are doing is we are getting a model of a IC, the I/O circuit of an IC, right? Now, when you are simulating a PCB, what happens is you will have traces on the PCB, you will have connectors on the PCB, and you'll also have wires that are there on the PCB to route the signal in the inner layers, right? So for modeling those structures and getting to know the parameters of those structures, we need another model which basically is called a S parameter model. So the S parameter model includes the losses associated and the performance associated parameters of wire or the traces on the PCB or any passive structures that are there on the PCB are specified by the S parameter models. Okay, so now S parameter models, if you see, this is a simple example of a S parameter model where at a specific frequency you have different parameters, and as seen in the table they are S11, S21 kind of, right? So these S parameter models, if you see by this table, these are actually frequency domain models. So you have various parameters mentioned at different frequencies, and these basically represent the actual performance of that particular structure for which we have the model, right? So in S parameter model, the S stands for scattered. Scattered meant actually reflected. So in S parameters, we talk more about the amount of reflections that happen in the PCB. So in S parameter models, there are actually four parameters. One is S21, as mentioned here, S12, S22, and S11. So to understand this, let us assume there is a DUT here. Okay, to this DUT, we have a input, and this input is connected to this DUT through some impedance, and we have output connected again. And so basically, we can assume these as two ports. Port 1, which can be assumed as first input port, and port 2 as another input port. So two ports, and then there is a DUT. Now for this structure, if we want to think of a analogy between in a PCB, what we can think is one port actually is a connector. Okay, so the connector will have an input, and then the input will pass. Let us assume there is another connector which passes at the output. So input from the connector passes through the out, and the signal passes through the PCB wires, whatever structures, and then passes to the output. So so assume two ports, right? In this scenario, there are inputs. There is some signal that is reflected back. So we have talked in the earlier scenarios, right? If there is an impedance mismatch that happens on a PCB, there will be reflections. Like example, if you have a wire, there will be a reflection. If you have some chip that is connected in between, there will be a reflection if the impedance doesn't match. So there are reflections on the PCB. So here in this diagram, if you see, in1 represents the amount of input, and out one here represents the signal that is reflected back. And when in1 is provided, out2 is the amount of power that goes into this port. So input is in1, output is out2. Similarly, and one is the reflection. And when you have in2 as input from this port, from the reverse side, you have out1 as the output going to this port, and out2 is the reflection. So this is how we have to read this diagram. And for this, when we see from the input side, we have parameter something called S21, which actually is named as forward voltage gain, which represents the ratio of the output transmitted power by input transmitted power. That means the amount of power that is transmitted on the output for a given input power. That's what the forward voltage gain mentions. And this is also called insertion loss. Right now we are talking about the gain. This S21 parameter can be shown in terms of loss. We will talk how to mention that in the next videos. But S21 can be mentioned in terms of losses, which we call it a insertion loss. Here we are calling it as forward voltage gain, for which it is a ratio of output by input. And then S12 is a scenario where first port is the output port and the second port is the input port. That means it is a reverse voltage gain, so which is out1 by in2, because input is from the reverse side. Okay, and then S11 is called input port voltage reflection coefficient, which represents the amount of signal that is reflected back, and this is actually represented by ratio of out1 by in1. Similarly, the output port reflection coefficient, which is mentioned as 2, it is out2 by into. That means when we give signal into, there will be some reflection because of impedance mismatch, which is represented by out2. So the ratio of out2 by into represents the output voltage reflection coefficient. So these are the 4 parameters. In the next videos, we will talk about what is insertion loss, what is actually return loss, and for a given structure, how the insertion loss, return loss matters, how much is the acceptable values, and for connectors, how it is represented. We will also see different connector manufacturer data sheets to see how they are represented, their models. Actually, we can look into them. So we'll talk about all these in the upcoming videos.